Hi everybody. So this next chapter is about limits and continuity. We talked a lot about these things back in chapter 3, so a lot of this we're going to be revisiting. Some of it's going to be new. Today we're going to talk about limits, and we talked about limits before as our function approached infinity or negative infinity. Today we're going to talk about limits as they approach a particular value. So this graph that we have right here, this is the function y equals sine of x over x. Actually, I don't want this at all. We're going to get rid of that. And so what I want to do in this case is I want to take the limit of this function as x approaches 0. So what I want to do is I want to find the limit of, let's actually call this f of x so that I don't have to write that all out. So the limit of f of x as x approaches 0. So that means I want to know what happens to my y values as my x values get closer and closer to 0 as I come at that x value of 0 from the left and the right. So if we think about little ants traveling on our curve as they get closer and closer and closer to 0, what is the y value they're getting closer and closer to? It might be kind of hard to tell, but if you look down here, we have this scale, and the y values are from -1 to 2, so this is 1 right here. So as the x values get closer to 0 from the left and the right, the y values get closer to 1, so we say that our limit is 1. Okay, we can confirm that also with our table. So when we look at our table, as our x values get closer to 1, right, from the left and the right, it says error there. So if we think about why it says error, is because if we were to plug 0 in here for x, we get a 0 on the bottom. So that's not allowed, but we can still find the limit. Limit just means what are we getting closer to as the x's get closer and closer to 0, what's happening to the y values. And you can see the y values are getting closer and closer to 1. So this function, sine of x over x, that's going to come up frequently just in our work in this chapter. And so we're going to write this down to refer to in the future that the limit as x approaches 0 of the sine of x over x equals 1. So this guy right here is going to keep coming back to haunt us, so we want to make sure that we're keeping that in the back of our minds. Okay, so in general, when we're finding the limit of a function, as x approaches that value from the left and the right, whatever number that we get for that value, we're going to call our limit. And that's basically what this is saying right here. So in general, we're going to call the value that we're approaching c. So the limit as x approaches c of f of x is going to be a value, and we're going to call that value L. So we're going to read that as the limit of f of x as x approaches c is L. Okay, all right, so let's flip. All right, guest teacher, feel free to pause at any time if you feel like you need to pause. All right, so these graphs right here are going to illustrate the fact that we can get a limit as you approach c, and it doesn't depend on whether or not the value is actually defined at c. So if in all of these, we're going to think about finding the limit as x approaches 1. So we want to find the limit of f of x as x approaches 1. Here's our function right here. So if we think about plugging 1 in here for x, if we did that, we would get a 0 in the denominator. And if we go back to what we talked about in chapter 3 and we factored, we would see, oh, that cancels, and we should be thinking, oh yeah, that's a removable discontinuity, and that's why it's just a line. But if we think about approaching 1 from the left and the right, so as I get closer to 1 from the left and the right, what's happening to my y values? They're getting closer and closer to 2. So even though there's a hole in the graph that's not defined at all, we can still say the limit is 2, right? Even though f of 1, right, if I plug 1 in, it just doesn't exist, even though f of 1 does not exist. Okay, so now this one is almost the same function, except for when x was equal to 1, it was defined that the y value would be 1. So it's like I have the same line, but then they just decided when x is 1, the y value would be 1. Now the limit, again, This is now the limit of g of x. And we're going to do it again as x approaches 1. Okay, so as I approach 1 from the left and the right, my y values are still getting closer to 2. Again, even though technically the y value at 1 is 1, not 2. That's still our limit. Okay, so even if it's not defined, even if that's not the y value at that particular x value, you can still find the limit. This is actually going to have, these not being the same is going to lead us to some continuity conversations later on. All right, now this last one, if I want the limit of h of x as x approaches 1, and we look at this function and there aren't any funky fractions. If I plug 1 in, I'm not going to get a 0 in the denominator. So the limit of this one is, if I approach 1 from the left and the right, my y value is still 2. And notice, if you were to just plug 1 in here for x, 1 plus 1 is 2. And that's really how we're going to first start out trying to calculate these limits, is we're going to first start by just trying to plug it in. And then if that doesn't work, we're going to try to look at the graph or the table. All right, so then next up we have these properties of limits. These are the same properties of limits that we talked about back in chapter 3, that if I have the limit of two things being added, I can separate it into the sum of the two limits, or the difference, or the product, or a constant, or whatever the case may be. So those are the same properties that we saw back in chapter 3 and also last semester in chapter 12 when we did sequences and series. All right, so example 3 is asking us to use any properties of limits to find any of these. So if this is a value, a number, or in this case just c, and I want to find the limit, literally all I have to do, and you're going to think that I'm making this up and it's not hard enough, all I need to do is just plug c into each of them. And what it's like I'm kind of doing is I'm taking the limit of each part individually, and so I can write it like this, and it kind of takes a little bit of time. But if I were to graph this and think, okay, as I approach any value, what is that y value getting closer to? It's just going to be getting closer to 3c cubed. And if I put the c in here, that's just going to get closer to 2c. And then if I go to put the c in here, there's nowhere to put it in, so it's just the limit of a constant is a constant. That is our answer. Again, it might seem like I'm trying to trick you, but that's really all there is to it. If you are taking the limit of something as it approaches a number, or in this case a variable, you are just going to substitute that in. Now if it were a number, you would evaluate it and see, what does that come out to equal. But in this case, we are just going to substitute the c's in, and that's it. Okay, and that's kind of what this second theorem is talking about. So the polynomial and rational function. So if you're trying to find the limit as x approaches c, you're going to find f of c. You're just going to literally plug c in. And same thing, even if it's rational, the only thing you have to watch out for is what if it's 0 in the denominator. Okay, so for example 4, if I want the limit of this function as x is approaching 3, I'm just going to substitute 3 in for x, and then I'm going to evaluate that. Okay, so this would be 9 times negative 1, so negative 9. Okay, so take a second and work on B and C. Okay, so you're going to go ahead, in this case you're going to plug the 2 in this case you're going to plug the 5 in. Okay, so everybody should be doing this right now, not just sitting there and waiting for the answer to magically appear, which it is going to, but you should still be doing it. So make sure you check those answers. Okay, so this next example is going to be kind of the same idea, but we're going to use some of the things that we know from before, from like trig. So if you look at, let's say this first one, and we use the trick where we just put 0 in for x, you're going to get a 0 in the bottom. And so what we want to try to do is somehow manipulate that so we don't get a 0 on the bottom. Okay, so I'm going to rewrite this as, first I'm going to just think of it as the tangent of x times 1 over x. So I just kind of split that apart. Instead of dividing by x, I wrote times 1 over x. And I did that because I know that I can rewrite the tangent as the sine of x over the cosine of x. So you got to remember way back to what, chapter 7 or whatever. Okay, so I'm going to come on up here. Now remember how I said that limit of the sine of x over x, that's going to keep coming back? I'm going to rearrange this. So I'm basically going to flip-flop these, which I can do because it's multiplication, and rethink of this as the sine of x over x times 1 over the cosine of x. Okay, I can do that because it's multiplication. If you think about it, if you multiplied across the top and the bottom in each of them, they would be the same. Okay, and now I can split this into the limit of the sine of x over x as x approaches 0 times the limit as x approaches 0 of 1 over the cosine of x. Now this we know from the very first example. We know that this approaches 1. This, I'm going to substitute the 0 in for x. So I want the cosine of 0. So, oh my gosh, now I have to remember the unit circle, right? Okay, 0 is here. Cosine, so that's the order pair 1, 0. Cosine is the x value. So this is 1 times 1 over 1, which is just 1. So this limit here is just 1 after all that work. Okay, now this next one, let's see, this next one, if I plug 0 in, is that going to give me a problem where, I would get 0 in the denominator? Now over here, I just took the cosine of 0, and it didn't give me a 0 in the denominator, so I can just go ahead and substitute the 0 in. Okay, so I have 1 plus the sine of 0. That means go to 0 degrees. The sine is the y value, which is 0. Cosine of 0 we just talked about is 1. Okay, so this one also is equal to 1. All right, so now this next one is asking you to use a graph to show that the limit does not exist. So in part A, you might look at that and say, wait a second, if I put 0 in, that's not allowed, right? I'm not allowed to have 0 in the denominator. And you might remember back from chapter 3 from our parent functions that this is a hyperbola that's been vertically expanded. So it looks something like this. So think about it. If you approach 0, so here's 0 right here. If you approach 0 from the left and the right, what's happening? Are you getting closer to a particular value? What's going on? So from the left, what's happening is you're going down to negative infinity. The right, you're going up towards positive infinity. So what's happening is you have a 0 in the denominator. It doesn't cancel. It's causing a vertical asymptote. Okay, and then the same thing, if you were to graph this one, so you can take a second if you want to graph it. I'm going to have at 2 a discontinuity, if you remember that from back in chapter 3. It actually has a slant, no, it doesn't have a slant asymptote. So it kind of goes like this, and then it goes like this. It looks really funny, but anyway, this is now the limit as I approach 2. As I approach 2 from the left and the right. So from the left as I approach 2, again, it's going down. I've got a vertical asymptote. As I approach 2 from the right, it's shooting up. I've got a vertical asymptote. So because there is a 0 in the denominator, and these, it's causing a vertical asymptote, which means no limit, or the limit does not exist. Okay, but remember, it doesn't necessarily always mean that, just because there's a 0 in the denominator that the limit doesn't exist, because we saw, up here in example 5, the limit did exist. So it's not just, plugging it in. It's sometimes a combination, right, of looking at the graph and maybe plugging it in. All right, we're getting there. All right, so now, as I'm talking about, approaching the number from the left and from the right, what I'm really talking about are what we call 1- and 2-sided limits. So we're talking about like the right-hand limit and the left-hand limit. So the limit as we approach a particular value c of a function from the right, the way we're going to show that we're approaching from the right is by a little plus sign. That's the notation we're going to use. So the limit of f of x approaches, oh, I can't read. The limit of f as x approaches c from the right. I can talk, I swear. All right, so then this one, we would denote that with the limit of f of x as x approaches c from the left. We're going to have like a little, it's going to almost look like a power that's a negative. So that means from the left, that means from the right. So this is our greatest integer function. Again, we talked about this guy back in chapter 3. And so if, let's say, we wanted to think about the limit of this as I approach 3 from the right, and the limit of this function as I approach 3 from the left. Okay, so here's my 3 right here. I'm going to kind of draw like a little dash line so we can see what we're trying to get closer and closer to. So sometimes people get confused so when we approach 3 from the right, that means on the right side of 3, so from this side, but you're kind of heading to the left because I'm heading towards the 3. So if I start to the right on this graph and then I head towards the 3, so I'm walking along here and then I have to jump down and I'm walking along here, and as I get closer and closer to 3, my y value is getting closer to 3. So that's my limit as I approach 3 from the right. Okay, now, as I approach 3 from the left, so here's my 3, here's the left, so if I start to the left and then I get closer and closer to the 3, the closer I get to 3, my y values are actually getting closer, not to 3 like the last one, but actually getting closer to 2. So if it so happens that the limit as you approach from one side is not equal to the limit as you approach from the other side, we say that the limit over all of f of x, just as you approach 3, does not exist. So in this case, we would say the limit of f of x as x approaches 3. So not with any power or anything up here, but the limit of f of x as x approaches 3, we say does not exist because the left and right hand limits are different. So basically, in order for a limit to exist at just a particular value, it has to be that the left and the right hand limits are the same. And if you look back to all the other ones that we talked about, if you approach from the left and right side, it was always that you got closer to the same y value from each of those sides. That's what makes the limit exist. And that is basically kind of what this says. I'm going to kind of rewrite it with this notation that we had used up here though. So what we want to say here is then that if the limit of f of x as x approaches c from the right is equal to the limit of f of x as x approaches c from the left, and that those both equal the same value, they both equal, let's say, L, then the limit of f of x as x approaches c, overall c, is also L. Okay, if it doesn't, if they're not the same, then the limit of f of x as x approaches c does not exist. And then usually if the limit doesn't exist, what that's going to mean is that there's some sort of discontinuity, and we'll get more into that in the future sections here. All right, so let's do some practice with that. Okay, so we're looking for limits at all these different values. So the limit at x equals 0. So here's x equals 0. And this means the limit of f of x as x approaches 0 from the right. So if I start to the right side of this graph and work my way towards the left to the 0, it's going up, it's going down, looks like some sort of hole in the graph, and then there's some sort of jump. But as I'm getting closer and closer to 0, what are my y values getting closer to? 1. Okay, so that's my limit. All right, for the next one, as I'm getting x equals 1. So here's x equals 1 right here. Okay, so as I approach 1 from the right, so again, if I start to the right and start getting closer to 1, my y values are getting closer to 1. Okay, as I approach from the left though, so on the left side of the graph, and I'm getting closer to 1, my y values are getting smaller and smaller, getting closer to 0. Okay, so since these are not equal, right, these are not equal, that means the overall limit of f of x as x approaches 1 does not exist. So I can find my right hand limit, I can find my left hand limit. If those are not the same, then I cannot find the limit at that value. All right, so I want you guys to take a few minutes and I want you to work on the rest of the examples. So these are all referring to this graph right here, and then A, B, and C in the A through E in the next part is referring to this other graph. Okay, so I want you to take a few minutes at your tables to think about what all of those limits would be. All right, guest teacher, you can go ahead and pause it, give them a few minutes to work on this, and then we're going to go over it. Okay, so hopefully you guys worked on this and were able to figure out these limits. Let's go over them quickly. All right, so we want at x equals 2, the limit as we approach 2 from the right and then from the left. Okay, so 2 is right here. So as I approach 2 from the right, so starting at the right, heading towards 2, my y values, they go up, they come down, they're getting closer to 1. Okay, as I approach from the left, they go down, they hop up, but as I get closer to 2, the y values are getting closer to 1. So since these are equal, that means that the limit of f of x as x approaches 2 is that value, it is 1. Okay. It is still it is discontinuous, and sometimes people get confused about that. They think they shouldn't be able to find a limit because it's discontinuous. So we will talk more about that in section 3, but we can still find the limit, even if there is that hole in the graph. Okay, so now at 3, so right here, as I approach from the right, my y values are getting closer to 2. As I approach from the left, my y values are getting closer to 2. Okay, again, whoops, these are equal. I notice up here I wrote that they weren't equal. I'm not sure why I did that. That should say equal. Okay, these are equal. That means the limit of f of x as x approaches 3 is 2. Right? And this one isn't discontinuous, right? We have a closed circle there. All right, and then this last one, it's the limit as I approach 4 from the left. So as I get closer to the 4 from the left, my y values are getting closer to 1. And that one just has the left hand limit. Okay, so let's look at this next one. So the limit of f of x as x approaches 0 from the right. So if I start to the right and get closer to 0, my y values are getting closer to 0. As I approach 2 from the right, so here's the right, well, I get closer to 3, but I can't actually get to 2 from the right. So we're actually going to say that that limit does not exist. I'm not sure if anybody out there was kind of wondering about that one, but the limit does not exist. Okay, now as I approach 2 from the left, so here's my 2, as I approach from the left, my y values are getting closer to 4. Okay, again, these are not equal, so we would say the limit of f of x as x approaches 2 does not exist. Oh, that was right here. There we go, right there. All right, and then this last one, the limit of f of x as x approaches 3 from the right. So here we go, from the right towards 3 is 0. Okay, so that's it. That's the crash course. Your homework is in the packet, very convenient for you, right? It's pages 8, 9, 10, and 11. It's a lot, but if you look on your calendar, we're spending the next 2 days on this. Okay, so right now, I want you to get as far as you can get. If you look at the calendar, you see that we're going to spend a couple of days on each of the sections. And we'll go over whatever questions you have in class tomorrow.